Okay, so this video is part 2 of basic concepts where we're going to talk about charge, current, and voltage. So charge being the most fundamental parameter that we are going to deal with in electric circuits. So charge, we're going to use the symbol Q to denote that when we write it mathematically, and again with notation from the previous video, when I write a script Q, it means it implies that it is changing in time. I could likewise write a capital Q, implying that the charge would be constant with respect to time. So charge comes in two polarities, positive. One of those that we know about is a proton, and a negative charge. And of course, those are electrons. There are other negatively charged particles as well, but we're going to be pretty much talking about the movement of these negatively charged electrons in this course. So charge is measured in units of coulombs, which is abbreviated with a capital C, where 1 coulomb of charge can be converted to a physical number of electrons, roughly 10 to the 18 electrons. Likewise, you could then determine the charge of a physical electron as being 1.602 times 10 to the minus 19 coulombs with a negative sign out front because it's a negatively charged particle. Okay, so current is charge in motion. Current is not the fundamental quantity, charge is, but current is particularly important in electric circuits. So it's charge in motion or time rate of change of charge. So in the last module, when we talked about time rate of change, we saw that was a first derivative. Likewise, it's going to be that case for current. So for current, we use the symbol I to describe current. And we know since it's a time rate of change, it's a first derivative of charge with respect to time. So I is going to be dq versus dt, and is going to be measured in units amperes, or capital A, which is therefore 1 ampere is equal to 1 coulomb per second. So to understand this, we could think of charge as being, or current as being, the total charge that moves through a given cross-sectional area for every second. Okay. So for example, let's visualize that. Let's consider a wire. We're just kind of blowing up this wire so that we can see it. Where inside this wire we've got a little slice that can count, and inside this wire it can count the movement of little electrons. So say we have all these electrons in here in this wire, and the electrons are moving this way, right to left. So in this case, since electrons are moving right to left, what we're going to do is we're going to define positive current I as being movement from left to right, and that's because we're moving negatively charged particles from right to left in this case. And so what current is basically a count of charges traversing through this cross-sectional area here in the middle. So the current describes the number of charged particles moving through that, and it implies that we know the direction of that charge. This is very important. It's current, in other words, must have both a direction and a value assigned to it. For example, given an arbitrary wire and with an arbitrary definition of I1, for example, And a second, also arbitrary definition of I2, shown in blue, for the statement that electrons in this wire are moving left to right at 1 milliamp. That's okay to say, that's a rate, millicoulombs per second. We could actually write the values of I1 as being negative 1 milliamp because I1 is moving left to right. Likewise, we could write I2 as being positive 1 milliamp. Both of these definitions are correct because we've not only assigned a value and a magnitude, but we've drawn a direction on the chart. So these are equivalent definitions. Okay, so current is our carrying capacity of charge. And we saw in the last module the definition of a circuit and a network. And so for a circuit, we know that it's a closed network. Since it's a closed network, it implies that we must obey the law of conservation of energy, which in this context means that although we can transfer charge around between sections in a closed circuit, that the total charge cannot change. So this is definition of charge conservation. It's really just energy conservation applied to the idea of a closed circuit. So one thing that's useful is often to plot the charge with respect to time, so that we can maybe understand also how that gets converted to current and other quantities that like power and voltage that we'll talk about later. So we're going to do a couple examples. Okay, so in this first example, what I'm plotting here is the charge, instantaneous charge is what I would call this, on the y-axis versus time. Okay, so charge is in units of coulombs, time is in units of seconds in this case. We see that at time 0, there is 0 coulombs of charge that we've observed through a wire, for example. It goes negative to -1 at 2 seconds, and then it looks like it starts going back towards the positive direction after that. So let's, in this case, find the current I with respect to time. So we could write this as a piecewise linear function if we wanted to. We could say, well, Q at time 0 is 0 coulombs, Q at time 1 is -1/2 coulombs, Q at 2 is -1 coulombs, Q at 4 is 0, Q at 6, for example, would be 1. Okay. So from 0 to 2, this obeys a function Q as a function of time as being -1/2 t, for example, and this is valid for t is between 0 and 2 seconds. And then from 2 seconds onward, we would have, so I should say here, qt equals a slope of 1/2 t, and of course a y-intercept of -2. So 1/2 t minus 2 would be our equation, valid from t greater than 2 seconds, out to infinity. Okay, and we know that I is just the first derivative of q with respect to time, so we're taking the first derivative of these expressions over these intervals. And we would see that I could be written as -1/2 amperes for 0 to 2 seconds and 1/2 amperes for greater than 2 seconds. And then plotting that, we would see that I is negative before 2 seconds and positive for greater than 2 seconds, and there's an instantaneous change at time equals 2 seconds. So what this means is that there's a change of direction in the current flow. So when the current flow is negative, we're accumulating what we think of as negative instantaneous charge. It's just the movement of charge in a particular direction. When we have positive current flow, shown over here, we're starting to accumulate more positive charge, in other words, charge in just a specific direction. Okay, so let's look at another example. In this case, plotting again charge, instantaneous charge versus time, we see that it's just a slope here of 2 coulombs per second. Okay, shown here in red. So what is the current? So again, current is the first derivative of charge with respect to time. First derivative of this, so this equation of Q would then be 2t coulombs. So the first derivative of that is just merely 2. In other words, IT, which we could rewrite as just capital I because it's constant in this case, is just 2 amps. So 2 amps of current continuously flowing through a wire would accumulate charge at the rate of 2 coulombs per second.